Good morning, everybody. Can you listen to me? Please raise your hand. Everybody, good morning. Yes, we are into DC circuit analysis. Today we can close it perfectly, sir. I am sure. Today we can close DC circuit analysis 100% perfect. Then tomorrow onwards it will be more interesting. Basics of time variance, where I will introduce inductor capacitor, and really things become more interesting. Okay, everybody, see quick review. Okay. Yes. Now see quick review what we did. Yesterday was a very big day, of course. See, we started day 9. We were doing actually superposition theorem. Okay, here number of subcircuits equal to number of independent sources, 3 subcircuits. First 10 volts only. I got current as 5 in the direction I choose. I took 20 volts only. Current is actually opposite to direction I choose, that is -5. And third case, because of 6 amperes, current is 0. So altogether, if you add, it is again 0. Then determine the power absorbed. Now, he is asking to find power by using superposition theorem. Now, power is a non-linear electrical parameter which we cannot directly find. Instead, we select a linear parameter like voltage or current. Yes, instead we select a linear parameter like voltage or current. Okay, and then we'll find power. Okay, so I took current, but because of 16 volt source, I dash I got. Because of 8 amperes, I double dash, and because of 16 amperes, I triple dash. And then I added all together. I is -2, and then power absorbed is I net square into R, that is 20 watts. Okay, now then find voltage Vx by using superposition theorem. Here again, the number of subcircuits equal to number of independent sources, but dependent source you should never touch. So subcircuit 1 only 10 volts, open circuit 3 let it be Vx dash, subcircuit 2 only 3 amperes, voltage source short let it be Vx double dash. Okay, then we got the answer. Then find current I by using superposition theorem. Okay, find current I by using superposition theorem. Now here also, though there is one dependent source, but number of subcircuits equal to number of independent source. So we took first 22 volts only, then I got 22 by 13 amperes, then I got 2 amperes only, then I got -4 by 13, and I took 5 volts only, I got -5 by 13. Okay, then altogether it is 1 ampere. Now these are important box models where linear resistive network excited by 2 independent sources. Okay, and he said when voltage source alone act, power is 25 watts, and when current source alone act, power is 9 watts. Determine the total power in resistance when both sources act simultaneously. Okay, when both sources act simultaneously. Again here, it is superposition theorem, but power is a non-linear. So I will talk in terms of currents. But because current directions also is not predictable, current directions is still not predictable as internal network is not given. So we have to take all possible directions. That is why I take plus and minus, plus and minus. Then we confirm that there are 2 possible answers. If both currents go in the same direction, power is 64 watts. But if one current direction opposes the other, it is only 4 watts. Both are technically correct answers. Then similar model I gave for 3 sources. Okay. Then here I asked what are the possible maximum and minimum power loss in resistance. Okay. Then yes, then we went to another box model where we are finding current by 2 sources. Each individual voltage source he gave, and he gave current, and total current when both are acting together he gave. So that also superposition theorem. But this is interesting problem where he did not suppress any source at a time. So here we have to apply that principle of linearity where this mathematical equation is giving everything, sir. Okay, this is the meaning of mathematical model of accepting superposition, linearity, homogeneity, and additive property for 2 inputs, and that inputs are current sources here. Okay, so from the given data we substituted, we got K1, K2, and then we got the Vx. Then in that regard, everybody, then in that regard, if E is 20 volts, yes, I1 is 5 amperes, V2 is 15 volts, and P3 is 12 watts. Then if E is 30 volts, then what are the currents, voltages, and power? Okay, yes, that way we did it here. Okay, that way we did. Then Thevenin's theorem, the most powerful of all. Thevenin's will convert any complex linear passive by linear active, sir. I won't even mention that linear active bilateral network into voltage source in series. Norton will convert into current source in parallel. Okay, then here category 1 only independent source. So I did lot of models here. Yes, lot of models. Category 1 is very easy because independent sources are easily suppressible. Okay, we can directly find resistance, and I did gate bits also. Okay, very interesting bits also I did. Then we came to category 2. Category 2 problems are both with independent dependent source. Here, dependent source resistance has to be considered, and moreover, independent source is already active. So here we cannot inject voltage or current. Instead, we do VOC by ISC. But follow passive notation here. And if only resistance, we can also do directly. But I gave a lot of gate bits. But these are important models. Dependent source problems are very important. In one problem, we got negative resistance. Look at this. This problem, we got even negative resistance. When can it happen? Negative resistance is a concept. When we model active regenerative networks like positive feedback networks, oscillator amplifiers, then we can do it. Okay, that is a very rare case, but answer is correct. Okay, which I gave negative resistance meaning. See, negative resistance meaning I gave here. Okay, then problems with only dependent source. Here only resistance exists. Okay, that models also I quickly did it. Okay, now that models also I did it. Okay. Then we came to special problems where even dependent source get affected because of circuit condition. In this case, you see, in this case, when dependent voltage source becomes zero, short it. And in this case, when dependent current source becomes zero, open it. That is the meaning. Then we came to maximum power transfer theorem. Yes, we proved that mathematically maximum power is transferred to the load when load resistance is source resistance. Okay. And during PMAX, one student asked this. During PMAX transfer theorem, efficiency is 50. See, simple, I gave this explanation here. See, suppose let us say the source is delivering some 100 watts. Because both are equal, RS is equal to RL, automatically this will consume 50 watt and this will also consume 50 watt. Okay, because both are equal. Suppose source is delivering total 100 watt, this RS will consume 50 watts and RL will consume 50 watts. So efficiency is output by total input. Now output is 50 watts only, but total input is 100 watts into 100. So it is 50% only. So during maximum power transfer theorem, the output efficiencies are very low. That is the meaning. During maximum power transfer theorem, the output efficiencies are very, very low. And how much it is? It is only 50 watts. Okay, that is the meaning. That is the meaning. And also, I gave another bit that during PMAX transfer, how much is the percentage of voltage drop across the load? See here also, because RS is equal to RL, like two equal resistors across source, voltage division rule, this will become Vs by 2. This also become Vs by 2. Like if total voltage is Vs and both resistors are equal, then this will become Vs by 2, Vs by 2. Nah. Yes, the voltage drop across the load will be 50% of the supply voltage. 50% of the supply voltage. Okay, that is the meaning there. Okay, nah? That is the meaning. Then we gave this, then we started this theorem. Okay, here only R we have to find. R is RTH. Okay, then here again I want maximum power directly. Okay, simple bit, sir. Then here balance bridge, we cannot transfer any power. Okay, this is direct question again, gate 1 mark. Here also Thevenin's theorem helped us directly. So this theorem is an application of Thevenin's theorem. This was interesting bit. Everyone see this bit. Yes, look at this bit, sir. In this bit, it is special that we are adjusting the loads source side. Listen, what is our original statement? See, when I come to original problem, yes, when I come to the original problem, original statement, we are adjusting the load to maximize power in the load. We are adjusting the load and maximize power in the load. Then Pmax occurs when load resistance is source resistance. Okay, that is our original statement. We are adjusting the load and also maximizing the power in the load. When load resistance is equal to source resistance, Pmax occurs. Okay, now. But here you see, we are adjusting the source to maximize power in the load. Then least source resistance will give highest power. That is what we proved. Okay, least source resistance will give highest power. Okay, now. Then I gave that options. See, in this options 2 is least answer, and in this option 0 is least answer. Then you see here similar IES bit where he is adjusting the source side, but the statement is very unique. He gave a normal statement saying that what is the maximum power transfer to the load. It looks very normal, but the thing is he is adjusting source side. Okay, na? And then you have to be careful. least source resistance will give highest load power, that you have to observe. Okay, na? Then in that regard, yes, for circuit shown, for what value of resistance are P max occurs in the load. Okay, for what value of resistance are P max occurs in the load. Okay, na? Yes. Here, in this case, R0 will give highest voltage, highest power. In this case, R infinity will give highest current and highest power. Okay, na? Yes. Now we will continue from there. Okay, now I'm continuing from there. Now this is a wonderful problem. Yes, very, very interesting gate question. Gate 2 marks question, but it is worth. The circuit represents an approximate DC equivalent of a battery charger. Okay, the circuit represents an approximate DC equivalent of a battery charger. Now, for what value of battery voltage E? Okay, for what value of battery voltage E, maximum power is transferred to the entire load network. Okay, the circuit represents an approximate DC equivalent of a battery charger. For what value of battery voltage E, maximum power is transferred to the entire load. Here load is not a single component. Here load is the entire battery charger circuit. Okay, here load is the entire battery charger circuit. This boxed yellow line is the entire load. So load is not a single component. Load is the entire battery charger circuit. This is the load. Okay, now you read the problem, everybody. The circuit represents an approximate DC equivalent of a battery charger. Okay, the circuit represents an approximate DC equivalent of a battery charger. Okay, now the circuit represents an approximate DC equivalent of a battery charger. Okay, then for what value of battery voltage E? Okay, then for what value of battery voltage E, maximum power is transferred to the entire load. Okay, then for what value of battery voltage E maximum? Guess it's a very interesting, simple problem if you know the logic. Just 1 minute, I'm giving, try it. Yes, see here, sir. See, in this case, what happened, na, sir? There is also battery. See, this yellow box line is a battery charger because this battery charger has a internal resistance and also there will be voltage regulator. Na, that voltage regulator resistance he gave because this is DC equivalent, na, sir. Because this is DC equivalent. Yes, because this is DC equivalent, he gave resistance equivalent actually. Okay, so this battery charger has a current limiting resistor. Okay, and also voltage regulator drop. Okay, this battery charger has a current limiting resistor and also voltage regulator drop. Please understand this. Okay, this battery charger has a current limiting resistor and voltage regulator drop. Okay, now we cannot neglect E and directly say load resistance is source resistance now. Please understand. We cannot neglect. Yes, we cannot neglect. Yes, we cannot neglect this battery and say load resistance is source resistance. We cannot do so here. Reduction not possible, sir. Reduction not possible. Then shortcut. What is the shortcut? That shortcut we just discussed just now. That what I told. Yes, what I told is under Pmax transfer theorem. See this point. See under Pmax transfer theorem. Yes, 50% of supply voltage will appear across the load. Whatever may be the load, 50% of the drop will appear across the load. So that is the idea here. So what I will do here, everybody observe. Yes, because we cannot reduce and directly argue load resistance is source resistance. But one thing we know, yes, but one thing we know under Pmax transfer theorem, 50% of supply will drop across the load. So if this really load is absorbing maximum power, then these terminals are the load terminals. So how much drop will occur? 50% of the source. Source is 20, na? This is 10 volts. So this is 50% of Vs. That is the logic. So now once you know this voltage is 10, now I'll write KCL. This current equal to this current plus this current KCL. So if you write KCL, incoming current 20 minus 10 by 10 is equal to outgoing 10 by 20 plus this is 10 minus E by 5 equal to 0. Okay, 20 minus 10 by 10, 10 minus E by 5. Okay, sorry, let me, incoming is equal to outgoing na. 20 minus 10, 10 volts by 10 is equal to this current is 10 by 20, this current is 10 minus E by 5. So this is nothing but 1 is equal to half plus 10 minus E by 5. So 10 minus E by 5 is half. That implies E is, yes, that implies E is, how much E is? That is nothing but 10 minus 2.5, 7.5 volts. 7.5 volts. So see, sir, how interesting this bit is. Okay, very, very interesting bit. Now, this is another gate bit. Very interesting. Again, logic fundamentals. The static VI characteristic. Okay, the static VI characteristic of network shown in figure A. The static VI characteristics of network shown in figure A are plotted in figure B. Static VI characteristics of network shown in figure A are plotted in figure B. Okay. What is the maximum power that can be okay drawn from the network? Okay. The static VI characteristics of network shown in figure A are plotted in figure B. What is the maximum power that can be drawn from the network? What is the maximum power that can be drawn from the network? Okay, this is figure A. And this is figure B. These are the characteristics. Okay. Of course, here I is in amperes and V is in volts. Okay. And this is something like, okay, this is something like 30 volts and this is something like minus 6 amps. Okay, see the question. The static VI characteristics of network shown in figure A are plotted in figure B. What is the maximum power that can be drawn from the network? Shall everybody try immediately? All the models I am covering at one place. The static VI characteristics of network shown in figure A are plotted in figure B. What is the maximum power that can be drawn from the network? What is the maximum power that can be drawn from the network? Okay, the static VI characteristics of network shown in figure A are plotted in figure B. What is the maximum power that can be drawn from the network? Chalo, 1 minute, everybody try. Yeah, see this time instead of giving network, he gave the characteristics. Okay, that is a logic here. Now, instead of giving the network, he gave the characteristics. See this VI characteristics at the terminals will give this. Now look at the common sense. What is the network having? Is it having only passive elements or active elements? Now look at the characteristics. Now there is a segment of characteristics appearing in fourth quadrant. See 1, 2, 3, 4. There is a segment of characteristics appearing in fourth quadrant means there is an active element inside. See, if characteristics go exactly through origin from 1 and 3, then it is purely passive. If characteristics go quadrant 1 and quadrant 3 from origin, then it is purely passive. Then it is purely passive. Yes or no? Then it is purely passive. But here, there is a segment of characteristics appearing in quadrant 4. So that means there is an active element inside. Yes, that means there is an active element inside. Please understand. There is an active element inside. There is an active element inside. Understood? Yes, there is an active element inside. Okay, everybody? Yes. Now, when there is an active element inside, everybody, chalo, when there is an active element inside, now we know Thevenin's theorem can convert. Thevenin's theorem can convert any linear active bilateral network. Yes, Thevenin's theorem can convert any linear active bilateral network into voltage source in series with resistance. Na? Chalo, I will reduce the box inside into Thevenin's equivalent. See, I will reduce the box inside into Thevenin's equivalent. Okay, I want to reduce the box inside into Thevenin's equivalent. I need this VTH and also RTH. Okay, yes. Now in the first observation, you take any operating point. Suppose I take this operating point. Now, if I take this operating point in the characteristics, what does it mean? Current is 0, voltage is 30. Current is 0, voltage is 30 means open circuit voltage. This operating point is current is 0, but voltage is 30. Okay, so if you observe, current is 0, but voltage is 30. Current is 0, but voltage is 30. So automatically VTH is how much? 30 volts. VTH is 30 volts. Okay. Then if I show the second, observation, this is again VTH, this is again RTH. Okay, this is VTH, this is RTH. Now you take any other operating point. Again, if I take the easy operating point here, yes, see this point. Voltage is 0, current is -6. See, voltage is 0, current is -6 means short circuit current. See, voltage 0 means shorted. Current is -6 to this direction. See, give direction entering box as a plus, that is direction. But -6 means ulta to this direction means it should leave. So this operating point will tell voltage is 0, current is -6. Voltage is 0, current is -6 means actual current is go this way. So voltage is 0, current is -6. Voltage 0 means shorted. Current is -6 means it is going this side. So what is other equation you can observe here? That VTH is equal to 6 RTH. 6 RTH. Okay. Now if you solve both, okay, then automatically RTH is going to be VTH by 6. That is 30 by 6. That is 5 ohms. So now we got Thevenin's voltage. Yes, and also Thevenin's resistance. Then P max is VTH square by 4 RTH. Simple problems are if you apply fundamentals. VTH square 30 into 30 by 4 into, okay, now VTH square is 30 into 30 because there is open circuit voltage by 4 into 5. So this is 5, 6 are, okay. This is 2, this is 3, and this is 15. So 15 3 is a 45 watts. 45 watts. So the only logic here is that instead of giving the network, he gave the characteristics. Yes, so we are linking the characteristics to model the network. But we know any complex network, including source. You may say, sir, why there is a source inside? Because there is a segment of characteristics appearing in which quadrant? Fourth quadrant. So pakka, there is a source inside. So I simplified like this, we got the answer. Okay, pakka, there is a source inside. I simplified like this is the answer. Okay, now that is a meaning there. That is a meaning. Okay, now that is a real meaning. Okay, now another model to conclude this theorem. Okay. What resistance connected between, okay, connected between terminals, okay, terminals A, B will draw maximum power, okay, power from the network, okay, and also find this Pmax. See what resistance connected between terminals AB will draw maximum power from the network, and also find this Pmax. This is I0 minus plus 8 I0. This is 10 ohm. 10 ohm. Okay, what resistance connected between terminals AB will draw maximum power from the network and also find this Pmax. Okay, what resistance connected between terminals AB will draw maximum power from the network and also find this Pmax. What resistance connected between terminals AB will draw maximum power from the network and also find this Pmax. Okay, now this is a very straightforward problem, sir. So here I am not only asking the resistance, but I'm also asking the value of Pmax. Okay, so what resistance connected between AB will draw maximum power from the network and also find this Pmax. Now this is simple Thevenin's category 2. Yes, this is Thevenin's category 2. In Thevenin's category 2, what we find VOC and ISC. If the question is only resistance, na sir, if the question is only resistance, then shortcut is there. Only resistance you deactivate. Deactivate means remove the 60 volts. If you remove the 60 volts, I0 becomes 0. If I0 becomes 0, dependent voltage source also becomes 0. If I0 becomes 0, dependent voltage source also 0, short it. But look from there, 10 in parallel to 10, answer is 5. If only resistance was asked, that is first statement, then I would have done directly. Because only resistance, what you can do, deactivate. Remove 60 volts, I0 becomes 0, dependent voltage source 0, short it. Then look from this side, 10 in parallel to 10, because this is independent mesh. 10 in parallel 10, answer is 5. But because he's also asking Pmax now, better do the original procedure. Better do the original procedure. That is nothing but VOC by ISC. Okay. If the question is only resistance, do like that. Okay. Deactivate and look from the terminals 10 in parallel to 10. But if the question is even the maximum power, I will do in a normal way. So this is like Thevenin's category 2. So step 1, first VOC. Okay, in step 1, what I'm doing, same problem. I will first find VOC. Okay, same problem. I'll first find VOC. Okay, this is 60 volts. 2 ohm, 3 ohm, 6 ohm, I0, minus plus 8 I0, 10 ohm, A, B. This is VOC. This is VOC. Okay, now I took A positive with respect to it. Now see, this, what is the only resistance seen from here? 2 is 2 plus 3 in parallel to 6. I told Nasa this is independent to this 2. These two meshes are independent to this. Okay, but this fellow is receiving energy due to some interconversion. So this resistance in is 2 plus 3 in parallel to 6. Again 2 plus 2, 4 ohms. 60 by 4, total how much? 15 amperes. Now 15 amperes will divide current division rule. This current will be, I0 will be total current into opposite 6 by some 9. So 90 by 9, 10 amperes. Now I0 is 10 amperes. This is 8 into 10, 80 volt. Now really 80 volt is seeing 20 ohms. 80 volts is seeing 20 ohms. This current is 4 amperes anti-clock. 4 amperes anti-clock. So when 4 amperes is entering this way, 4 tens are 40 volt. 4 tens are 40 volt. Okay, na? Yes, 4 tens are 40 volts. Then this will become minus 40 volt. This will become minus 40 volt. Okay, now this will become minus 40 volts. Okay, yes, this will become minus 40 volts. Okay, then step 2, ISC. Step 2, ISC. Okay, yes, when I go to ISC, now see the same problem. The same problem. Okay, I'm shorting this. Watch this. Okay, same problem. I'm shorting this. Okay, to find ISC. Okay, this is of course A. This is of course B. This is 60 volt, 2 ohm, 3 ohm, 6 ohm. This is I0. This is again 8 I0. This is 10 ohm. And I need what? I need what? ISC. If A is positive with respect to B, passive notation, this is ISC from A to B. Okay, na? But why I removed these 10 ohms? This 10 ohms I removed because it is shorted. Okay, this 10 ohms I removed because it is shorted. Now again, sir, resistance seen by this is 460 by 4, 15 amperes. 15 will divide, it is going to be 10 amperes. Now this is 10 into 8, 80 volts. Then automatically this current is 80 by 10, 8 amperes anti-clock. If it is 8 amperes anti-clock, so ISC is minus 8 amperes. ISC is minus 8 amperes. ISC is minus 8. So now automatically, yes, now so automatically this RAB is RTH. That is VOC by ISC. VOC is minus 40. ISC is minus 8. Which quadrant it is? Both voltage negative, current negative means third quadrant. Third quadrant means sync only. It is plus 5 ohms. Sync only, no problem. Negative resistance is not coming here. Follow the notations, that is very carefully, sir. VOC is minus 40, ISC is minus 8. Ratio is again plus 5 sync. So now, yes, Pmax value is VTH square by 4 RTH. Here pure Thevenin's theorem, then only this formula can be applied. So VTH square 40 into 40 by 4 into RTH 5. Overall, it is nothing but 80 watt. 80 watt. Okay, na? That is why you see this resistance also we can get directly, sir. If the question is only resistance, I told how to do. If the question is only resistance, I told how to do. Yes, if the question is only resistance, then deactivate. Okay, then deactivate. You remove the 60 volts. Then I not becomes 0. I not becomes 0. Dependent voltage source also becomes 0. Dependent voltage source 0, short it. Then 10 in parallel to 10, 5. Same 5 will come. Okay, but procedure we did. Okay, na? Chalo, with this we completed another major theorem. Now we are coming to theorem number 6. Okay, theorem 6, that is Theligun's theorem. Very small but powerful. Theligun's theorem. Okay, Theligun's theorem. Okay. Now what is this Theligun's theorem? Okay, what we can learn. Very interesting. Theligun's theorem. Okay, na? Yes, this theorem is about verification of law of conservation of energy. Law of conservation. Okay, law of conservation of energy. Okay, na? This theorem is about verification of law of conservation of energy. However, in any linear time invariant network, okay, however in any linear time invariant network or system, okay, we can also okay, verify this theorem by measuring okay, instantaneous power. See, actually it is law of conservation of energy only, sir, but since energy is integral power dt, okay, since energy is integration of power or power into time in joules, so I can verify law of conservation of energy directly, or in any linear time invariant system we can also verify this theorem by measuring instantaneous power. Okay, na? By measuring instantaneous power. Okay, na? By measuring what? Instantaneous power. Okay, so power at an instant. See, energy over a period is power at an instant. That is what I'm trying to say. Actually, it is law of conservation of energy only, sir. No one can violate. Energy can either be created or not destroyed, but you can convert or transform into different forms. But in time invariant steady state network, na, sir, we can also measure power at an instant and prove it. That means what we have to prove, that is power delivered by the sources is power absorbed by the sink. So either energy over a period or power at an instant. So here in this theorem, okay, we need to mathematically verify okay, sigma vk ik equal to 0, where k is taking the value from 1 to b, where b is the number of branches. Okay, where what yes, where b is the number of branches in the network. Okay, that is nothing but yes, sigma vi of sources, that means power delivered by the sources. Okay, that is power delivered by the sources equal to sigma vi of sinks, that is power absorbed by sinks. Okay, see, very easy, sir. Everyone look here again. It is not sort of very easy, simple theorem. See, the question is, this theorem is about verification of law of conservation of energy. However, in any linear time invariant network or system, we can also verify this theorem by measuring power. Actually, it is energy over a period is nothing but power at an instant. So rather than taking 10 seconds, 100 seconds or 100 days in a steady state network, okay, in a steady state network, what I will do, I will measure the power at an instant and prove it. Okay, na? That way, yes, I need to prove sum of powers in all the branches are 0. There is now power delivered by sources, power absorbed by sink. Now I'm writing note. one. Note one. This Telegun's theorem. Okay, this Telegun's theorem is the only theorem. Okay, in electrical circuit analysis. Okay, this is the only theorem in electrical circuit analysis which is also valid. Yes, which is also valid for any non-linear element or network. Okay, this is the only theorem in electrical circuit analysis which is also valid for any non-linear element or network. This is the only theorem in electrical circuit analysis which is also valid for any non-linear element or network. Okay, now that is the first thing. Okay, then while applying this theorem, the topological arrangement of network should not be altered, should not be disturbed. I will write like this: disturbed. Okay. However, we can still verify. Telegun's theorem. Okay, Telegun's theorem independently for the subcircuits, for the network, either before reduction or after reduction. Okay, either before reduction or after reduction. I will explain, sir. Now, third point. Very interesting that Telegun's theorem is very interesting. Telegun's theorem can also be verified. For any linear time invariant network. Okay, Telegun's theorem can also be verified for any linear time invariant network, but for time variance. In the input excitations. But for time variance in the input excitations, where we can mathematically prove sigma Vk T1 into Ik T2, sigma Vk T2 into Ik T1. Of course, K is for the number of branches. So here automatically V is the number of branches in the network. Okay, and T1, T2 are two different instances in time. Okay, measuring voltages and currents in network. Okay, T1 and T2 are two different instances in time measuring voltages and currents in the network. Okay, T1 and T2 are two different instances in time measuring voltages and currents in the network. Okay, measuring voltages and currents in the network. I will explain, sir, everything I will explain. Okay, so just everyone see what I'm trying to say. See, maximum power transfer theorem is also, sir, all models I covered. Okay, all models I covered. Now this is called Telegun's theorem. Telegun's theorem is nothing but law of conservation of energy. It is also valid in every problem, but we are now specially learning here. That does not mean in all the previous classes it is not there. It is there everywhere. No one can violate law of conservation of energy. But energy is power into time. So rather than measuring energy over a period, but I am measuring power at an instant. Okay, rather than measuring energy over a period, I am measuring what? Power at an instant. Okay, that is what I am trying to do. Power at an instant. So I need to verify sigma powers for all the branches is zero, but there is nothing but power delivered by source is power absorbed by sink. Now some points. This is the only theorem in the world in my subject which is valid for any nonlinear element or network. So even op-amp network, diode network, transistor network, okay, you go to thyristor network, no one can violate law of conservation of energy, na sir. That is true. And also while applying this theorem, don't do reduction. Don't compare energies and powers from previous network to next network. Like that you cannot do. Some students do such mistake. Given problem, they will change and they will argue, sir, I'm not getting answer. No. See, that is why while applying this theorem, the topological arrangement should not be disturbed. So don't do. If you disturb the network, then automatically effective resistance will change and currents and powers also will change, na, sir. So like that, you should not compare the given network to the other network. Either you take any one network, either before reduction or after reduction. That is what my argument is. Take any network, sir. Either you reduce completely or you don't reduce. So for that, we can prove this theorem. But don't do intermediate reduction and say, sir, I'm not getting answer. Okay. That is why I wrote that while applying this theorem, the topological arrangement of the network should not be disturbed. Okay, na? The topological arrangement of the network should not be disturbed. Should not be disturbed. Okay, na? However, we can still verify this theorem. Okay, however, we can still verify this theorem independently for the network either before reduction or after reduction. Okay, na? Then Teligans theorem can also be verified for any LTI network. Yes, Teligans theorem can also be verified for any LTI network. Okay. Yes, Teligans theorem can also be verified for any LTI network, but for time variance in the input excitation. Okay, but for time variance in the input excitations, where we can mathematically prove. Okay, yes, mathematically prove this. Voltage at first instant into current at second instant, into voltage at second instant into current at first instant for all the branches. Very interesting, sir. I will prove this. Wait. Okay, na? Chalo. Okay, now, sir. Chalo, I am going with the first classical problem to understand the capability of this theorem. Chalo, I am writing this question. Verify Teligans theorem for network below. Verify Teligans theorem for network below. Okay, this is 1 ohm, 2 ohm, 3 ohm, 4 ohm. This current is Ix. Then this is 2Ix. This voltage is Vx. And this is 3Vx. 3Vx. And this current source is 22 amps. Chalo, sir, everybody verify Teligans theorem for this network shown below. Verify Teligans theorem for the network shown below. Okay, na? Yes. Now, sir, what is that we have to prove? We have to prove that. Yes, we have to prove that total power delivered by source is power absorbed by the sink. Okay, we have to prove that total power delivered by the source is power absorbed by the sink. Okay, na? Please understand. Total power delivered by the source is power absorbed by the sink. Okay, na? Now, resistors are always sinks, sir. Here resistors are okay, 1 ohm, 2 ohm, 3 ohm, 4 ohm are direct. They are resistors, na, sir. No issue. but there is one independent DC current source and two dependent sources. One independent DC current source and two dependent sources. Now, how can you declare their source and sink directly? You cannot declare like that, nah. You cannot declare. So that is why it is a very big conventional problem. So I'm asking you to prove. See, if I give small problem, Maza won't come, sir. So in this problem, proving Teligans is a big challenge. Now, what you do, everyone? So because we don't know how these sources will depend, either dependent or independent, how they are behaving, whether source or sink, we cannot tell. Resistors are always sink, no doubt. But this independent DC current source and dependent sources, we cannot directly declare. So what I will do, yes, here you cannot do any reduction. See the second point, topological arrangement should not be disturbed. You cannot do any reduction, sir. As it is, we have to prove. So for that, what you do now, sir, determine all the elemental voltages with correct polarities and all the elemental currents with correct direction. I want all the elements voltages with correct polarities and all elements current with correct direction. Okay, that means completely big problem. So I will say, okay, I'm writing a solution here. Okay, I'm writing here. Use mesh analysis first. Mesh analysis to find all elemental voltages with correct polarity and currents with correct direction. Then we will declare which is source and which is sink. Because in a source we know current leaves positive terminal of element, and in a sink we know current enter positive terminal of element. Okay, we know in a source current leaves positive terminal of element. Okay, and in a sink current enters the positive terminal of an element. Okay, now in a source we know current leaves the positive terminal, in a sink current enter positive terminal. Okay, like that we can do. Okay, now that way we can do. That way we can do. Okay, now that way we can do. Chalo, sir, I want everyone to write mesh equations. Chalo, everybody write mesh equations. First, I will give the notation mesh equations I want. See, this is current I1, this is current I2, this is current I3. So there are three standard mesh equations plus two link equations because there are two dependent sources. Now. One link equation between Ix and I1 and second link equation between Vx and I2. Chalo, do it, sir. I'm giving you 2 minutes. Write mesh equations, everybody. Please write. Yes, everybody see here now. I just asked you to write mesh equations. Okay, na? Chalo, I am writing the first mesh equation. Okay, starting from here. 1 into I1 plus 2 into I1 minus I3 super mesh plus 2ix plus 3I2 equal to 0. That is the first equation. Second equation difference I2 minus I1 equal to 22. Third equation I3 is minus 3Vx. Okay, then link equation. What is the link equation? Ix is minus I1. Okay, then Vx is 3I2. Okay, yes, Ix is minus I1. Vx is 3I2. Okay, na? So that is the meaning here. Okay, now I'm solving them, sir. See any doubt you can ask, look at the equations. First is a super mesh. Second is the difference equation. Third is a comparison equation. Link equation Ix is minus I1 and Vx is 3. So now I'm solving them, sir. See, I'm solving. Solve them. So what I will do first, I substitute Ix here. Minus I1, this will go I1 plus 3I2 minus 2I3. I1 plus, okay, I1 plus 3I2, 3I2 minus 2I3 equal to 0. That is the first equation. Then second, minus I1 plus I2 is 20. Minus I1 plus I2 is 20. Third, Vx if you take here, total 9I2 plus I3. 9I2 plus I3 is 0. 9I2 plus I3 equal to 0. So now again, first I will add these two. Okay, this if you do add these two, then this becomes 4I2 minus 2I3 equal to 0. Okay, 22. Yes, if I add these two, 4I2 minus 2I3 equal to 22, then I will multiply this by 2 times. 18I2 plus 2I3. 2I3 equal to 0. Now finally, if you add these things, 22I2 is 22. So I2 is 1 ampere. So first thing we got I2. Now once you get I2, from this directly I3 is how much? Minus 9. I3 is how much? Minus 9. Very good. We got this also. Then what is I1 then? Yes, we'll substitute to get I1. Okay. Yes, in this only if you substitute I1 will be I2 minus 22. I2 minus 22 is minus 21 and that also we got. Then extra Ix. See what is Ix link equation? Ix is minus I1. So Ix is minus I1. Minus of this is plus 21 amperes. Plus 21 amperes. Then what is Vx? Vx is nothing but 3I2. 3I2. That is 3 times of this. 3 volts. 3 volts. So we got everything. Okay, we got everything. Okay, now I'm substituting this. Now this is important, sir. That is why I told you this is a conventional problem. Now substitute in the network. See very carefully, I'm writing the network. Everybody watch this. I'm substituting everything in the network now. Everybody watch this. 1 ohm, 2 ohm, 3 ohm, 4 ohm, 22 amperes. This is Ix. 2Ix. This is Vx. 3Vx. Okay, 3Vx. Okay, now. So I'm substituting. First of all, mesh currents I1, I2, I3. How much I got? I1 is minus 21. So I1 is minus 21 means anti-clock 21. Anti-clock 21. Then I2 is how much? Plus 1. Plus 1 means clockwise 1. Clockwise 1. I3 is how much? Minus 9. Minus 9 means anti-clock 9. Then Ix, Vx. Ix is 21 amperes. So directly this also become how much? 21 amperes. 21 amperes. Okay. Then once Ix is 21, this is a dependent voltage source now. This is 2 Ix volts. 2 Ix volts means 2 into 21, 42 volts. 42 volts. Then Vx is 3 volts. Okay, Vx is 3 volts. Okay, Vx is 3 volts. Okay, Vx is 3. If Vx is 3 volts, there is a voltage dependent current source. This automatically become 9 amperes. 3 3s are 9 now. Yes, this becomes 9 amperes. Yes, this becomes 9 amperes. 9 amperes. Okay, and this is already 22 amperes. This source is already how much? 22 amperes. Chalo. Now with this data, yes, with this data, I will now find all the elemental voltages and currents. Okay, chalo. Now in external branches, mesh currents are branch currents. So this is 21, this is 21, this is 1. So this is also 1. This is also 1. And this is 9, this is also 9 amperes. This is also 9 amperes. So this is 21, this is 1, and this is 9 amperes. Okay, and this is 22. Okay. Now in this branch, this is 9, this is 21, this is 9, this is 21. This total become how much? 21 minus 9. That is 12 amperes. This is 9, this is 1. This total become 10 amperes. 10 amperes. Okay. Yes. Now I got all the branch currents. You see the yellow current I got. See with this mesh currents only I got everything, sir. See this is 21 anti-clock I1. So this is also 21. This is 1. This is 9. But these branch currents, these common branches are different now. See, this is 9 this way, 21 this way, 9 this way, 21 this way. Difference is 21 minus 9, 12. Here in this branch, you see 9 this way, 1 this way, 9 this way, 1 this way, total. This is 22. Okay, now? So we got everything. Okay, we got everything now. Now, in that regard, once we got the branch currents, yes, once we got the branch currents, okay, now I can find the branch voltages. Okay, I can find what branch voltages I can find. Okay, now I can find branch voltages. So now mesh current data is over. Now I can remove this mesh currents. Chalo. Now, yes, if I write the branch voltages, yes, everybody. Chalo. This is 21 into 1, 21 volt. This is 12 2s are 24 volt. This is 9 4s are 36 volt. Yes, still this voltage. Now you write a KVL here. This is 24, this is 21. So 24 plus 21, this is 45 volt. And for this also you write a KVL. See, minus 42, minus 42 plus 24 and minus 36. See, minus 42 minus 36 is coming how much? Minus 42 minus 36 is, yes, minus 78. Minus 78 plus 24 is plus 54. So this will be plus 54. Yes, all voltages also I got. Chalo, by using KCL, KVL, I got all the voltages currents. Now, see, sir, that is a big problem. So this network, after doing so much hard work, mesh analysis, mesh currents and branch currents, now this problem is being observed with all the voltages and currents. Now you can declare which is source and which is sink. Chalo, see, resistors are always sink. Resistors are always sink. Now you see this independent current source 22 is there na? Independent current source, current is leaving positive terminal. It is a source only. Then this dependent voltage source is a sink, current enter positive. And this dependent current source is a source. So this independent current source and this dependent current source are both sources. This independent current source and dependent current source are both sources. And this dependent voltage source is a sink. Now I can prove. Yes, now I can prove. Okay, sigma power delivered by the source. Okay. Yes, one is voltage into current. 45 into 22. Yes, one is voltage into current. 54 into 9. Because these two are only acting like sources. Okay. Then remaining all sinks. Power absorbed by sinks. Resistors, first of all, voltage into current in 1 ohm in 2 ohms. Voltage is 24, current is 12 in 3 ohms. Voltage is 3, current is 1 in 4 ohms. Voltage is 36, current is 9. And finally, this dependent voltage source, voltage is 42, current is 10. Current is 10. That many watts. That many watts. Okay. Power delivered if you do, that is this. And here power absorbed also you do, that you will get this. Now you check, sir. Now you check mathematically. Yes, you check mathematically. Yes, you will get this as 1476 watts. This also 1476 watts. Then your answer is correct. That is why it is a lengthy problem, sir. IS conventional model. Small problem, you will never get the maza, I'm telling you. Small problem, you will never get the maza of doing this. Okay. Yes, small problem, you will never get the maza. But after doing this, yes, now I confirm. Yes, now I confirm that really, yes, Telighan's theorem is verified. Now I proved indirectly that total power delivered by source is power absorbed by sink. Total power delivered by source is power absorbed by C. Okay, that is the meaning. So now I'm giving interesting question here. IAS objective. Okay, the power absorbed. Okay, the power absorbed by each element in order is dash. The power absorbed by each element in order is dash. This is 1 volt. This is 1 ampere, and this is 1 ohm. Okay, this is 1 volt, 1 ampere, 1 ohm, and power absorbed by each element in order is as the power absorbed by each element in order is dash. Okay, na? So the power absorbed by each element in order, the options are okay, 1 watt, 0 watt, minus 1 watt, option B, minus 1 watt, 0 watt, less 1 watt, option C, 0 watt, minus 1 watt, less 1 watt, and option B, 0 watt, 1 watt, minus 1 watt. Okay, in order means the elements are arrangement. Okay, the power absorbed by each element in order, left, middle, right. These are the options. Take the correct option, everybody. 1 minute. Yes, here, everybody. Power absorbed by each element. Yes, see. See, that is why in this problem you are not supposed to disturb the topology. See, that is why I want to say. See, you may say, sir, this current source is in parallel to resistance. Can I convert into voltage source in series? Technically, that is possible. But when you are proving this theorem, you are not supposed to disturb. Otherwise, these answers won't match. You can still verify Telighan's theorem even after reduction. But these answers won't match if you do any topological reduction. See, that is why this point, see, at starting I gave this point. Yes, while arranging second point, you see the second point. While arranging the theorem, while applying this theorem, the topological arrangement should not be disturbed. However, we can still verify Telighan's theorem independently, either before reduction or after reduction. So that is why, sir, here don't say I will now convert this current source in parallel to voltage source in series. No, you are not supposed to do that. Okay, so as it is, we have to find. Now listen carefully, sir. This is first of all parallel system. In parallel system, voltage is same. So this is plus and minus 1 volt because in parallel system voltage is given na. So this is plus and minus 1 volt. So automatically this is plus and minus 1 volt and this is also plus and minus 1 volt. Voltage is fixed. Now automatically in a passive element, if this is 1 volt across 1 ohm, this current is 1 ampere. When 1 volt is across 1 ohm, this is clearly 1 ampere. Okay, when 1 volt is across 1 ohm, this is clearly 1 ampere. Now see here, this is 1 ampere and this is also 1 ampere. So KCL satisfied. This is 1 ampere, this is 1 ampere. So here no current cannot flow, because KCL already satisfied, sir. This is 1 ampere, this is 1 ampere. No current can flow. That means this voltage source is interesting. This voltage source is developing voltage for the network to one, but it is not supplying any power. This voltage source is developing the voltage for network to work, but it is not supplying any power. So now conclusion is this is neither source nor sink. This is neither source nor sink. So power absorbed is 0 watt. Now this is source. Clearly this is a source. And power absorbed. Source will not absorb now minus 1 watt. Okay. And this is really a source. This is not a source. Okay. This is source. So power absorbed is negative. But this is sink. 1 ohm is sink. 1 ohm is sink. So power absorbed is positive 1 watt. See, sir. First of all, parallel system voltage is fixed. So 1 volt, 1 volt, 1 volt. Now in a passive element, if 1 volt is across 1 ohm, current should go down because current should enter positive terminal. Now here KCL satisfied. 1 ampere, 1 ampere. KCL satisfied now 1 ampere, 1 ampere. Okay, this should not deliver anything. So this is neither source nor sink, power absorbed 0. This is a source. Power absorbed is negative. This is a sink, power absorbed is positive. So answer is 0 minus 1, 1. Answer is 0 minus 1, 1. Okay, now there is a meaning there. Okay, so I am giving another IAS objective. Okay, power delivered by each element in order is dash. Okay, power delivered by each element in order is dash. Power delivered by each element is in order is dash. Okay, power delivered by each element in order is dash. I am writing the brackets, write the answers in the order, left, middle, right. Okay, I will also give another question IAS objective, Okay, I am giving another question in IAS objective. Yes, here again, the power absorbed, okay, by each element in clockwise direction from P to Q terminal. Is dash. Okay. This is Q. Okay. The question is, Writing here in brackets. So now see the question. Power absorbed by each element in clockwise direction from P to Q. So P to Q. That means first this, second this, third this. So to answer these both questions, read the question and write the answers immediately. Yes, see the answers now, everybody. See the answers. We'll take a break now. We'll see the answers now. See power delivered by each element in order. See power delivered by each element in order. First, let us declare which is source and which is sink. See again, this is a parallel system. Voltage is same. So between these two nodes, okay, between these two nodes, voltage is same. This is 6 volts. So this is also 6 volts. This is also 6 volts. Now in a passive element, if this is 6 across 3, this has to be 2 amperes. This has to be 2. Current should enter positive in a sink. And now this is already 5. Okay, now out of 5, 2 went. KCL. Out of 5, 2 went. So this has to be 3. Now see here now. This is source or sink. This is source, sir. Current is leaving positive terminal, not source. Current is leaving positive terminal, so power delivery is 6 5 are 30 plus 30 watt. Now this is a sink, sir. This is a sink. 3 ohm is sink. Power delivered is negative. Okay, negative minus 12 watt. Okay, V into I minus 12 watt. Yes or no? This is minus 12 watt. Minus 12 watt. And then this is again a sink because current is entering positive. Sink cannot deliver. So power is minus V into I minus 18 watt. Minus 18 watt. So sigma P is however 0. You see, add these three plus 30 minus 12 minus 18 is 0. Yes, sigma P is 0. That is Kelvin's theorem. Previous problem also you see sigma P is 0. You see sigma P, if you do sigma P is 0. Plus 1 minus 1 0. Here also same. Sigma power delivered is 0. Here sigma power absorbed is 0. Okay, but here you see now The power absorbed by each element in clockwise direction from P to Q is dash. Now here is series system. Series system, what is same? Current is same. Series system, current is fixed. So this is 3 ampere, this is also 3 amperes, and this is also 3 amperes. This is also 3 amperes. Okay. So when this is 3 amperes going through 4 volt, 4 ohms, yes, going through 4 ohms. This is 4 3s are 12, passive notation. Now this is 12, this is 12. Interesting, sir. This is 12, this is 12. No voltage here, no voltage here. Again, yes, again, this is neither source nor sink. Neither source nor sink. So power absorbed is 0 watts. Now this is source. Power absorbed is minus 36 watts. And this is sink. Power absorbed is plus 36 watts. So answers are 0 watts minus 36 plus 36. Again, sigma P is 0. That is Theligen's theorem. Again, sigma P is 0. That is nothing but what? Theligen's theorem. Okay, Theligen's theorem. So we will take a break of half an hour. It is 8:45. So 9:15 come back. Yes, welcome back everybody. Are you there? Please come back. Are you there? Please come back everybody. Raise your hand. Can you listen to me? Raise your hand. Yes. Okay, now I will give gate problem in this Teligans theorem. This is a gate bit. Easy 1 mark, sir. If power absorbed is power absorbed, yes, if power absorbed by the battery is 10 watts, okay, is 10 watts, then determine its voltage E. Okay, then determine its voltage E. Okay, if power absorbed by the battery is 10 watts, then determine its voltage E. So this is some 20 volt, 10 ohm and E. Okay, chalo, get bit 1 mark. If power absorbed by the battery is 10 watts, then determine its voltage E. Everyone do it now. Now see this, sir. Power absorbed by the battery. So power is absorbed by the battery means then this is source or sink. This has to be sink. Yes or no? If this has to be sink, current should enter positive or negative terminal of the battery. Current should enter the positive terminal of the battery. So power absorbed by the battery means it is a sink getting charged. So current should enter positive terminal. That means the mesh current here will be clockwise now. And also he gave that this E into I is 10 watts because he said yes, power absorbed by the battery. Okay, that is 10 watts. But with that E into I 10, you cannot declare E, na sir. So many answers will come. Now according to Teligans theorem, okay, total power delivered by the source is power absorbed by the sink. Now here clearly after declaring the current practical direction, because it is a sink, now which is the only source? 20 volts is the source and remaining 2 are sinks. So this 20 into I is equal to I square into 10 plus E into I, because this 20 into I is the source, sir, and remaining are sinks. 10 into I square into R, 10 and I square into 10 and E into I. No, but already this E into I, how much he gave? This 20I is 10I square plus E into I is how much? 10. Yes, E into I is 10. Now you can observe that here clearly, yes, here I equal to 1 ampere will satisfy, yes or no, will satisfy the equation. Okay, here I equal to 1 ampere will satisfy the equation. I equal to 1 ampere will satisfy the equation. Yes or no? I equal to 1 ampere. So automatically E into 1 ampere is 10. Okay, E into 1 ampere is 10. So E is 10 volts. 10 volts is the answer. Okay, very simple. But Kelvin's theorem is indirectly coming. Okay, na? 10 volts is the answer. Now another important property of Kelvin's. Now this question is that, okay, verify Kelvin's theorem for LTI network shown. That means linear time invariant network shown. But for time variance in the input excitations, but for time variance in the input excitations, okay, but for time variance in the input excitations referred at two different instances in time as shown. So this is network at time t1, network at time t1, and this is network at time t2. It's the same network, sir. Network is same, but I'm referring at two different instances. Let us see what are the things changing here. Network property is linear time invariant, but excitations are changing, which I gave you as third point in the note of this theorem, which I will read again. See the very interesting property of Kelvin's theorem here. 10 volts, 1 ohm, 2 ohm, 2 ampere. 20 volts, 1 ohm, 2 ohm, 4 ampere. Okay, it is same network, sir. Same network, but excitations are doubling. For simplicity, I took only double, but you can take one double, one triple, one reverse direction, one positive voltage. Any way you can take. See, verify Kelvin's theorem for linear time invariant network shown, but for time variance in the input excitation. But for time variance in the input excitations, referred at two different instances in time. Now see, I gave a very important property of this theorem. You see this. Kelvin's theorem can also be verified in a linear time invariant network, but for time variance in the input excitation. Network is same, but excitations are changing, where we can prove mathematically that sigma VKT1 into IKT2. That means voltage at first time into current at second time for all branches is equal to voltage at second time into current at first time on all branches. That means here, okay, this is the same network, but at two different times we are referring. That means let us say this voltage has doubled here, this current has also doubled. Or you can take any value, sir. Answer concept will come. Now what I have to prove? All voltages at first time into current at second time in second network is equal to all voltages at second time into currents at first time. So now what you do, everybody? Yes, first find all voltages and currents with correct polarities and directions. Everybody, both networks. 1 minute you do it. So find all the elemental voltages with correct polarities and currents in correct direction immediately. Then I will prove this point. Okay, do it immediately. And there are 4 branches here. Yes or no? 1, 2, 3, 4. Same network. 1, 2, 3, 4. 4 branches. So here we know branches are 4. Branches are 4. So what we need to verify? We need to verify. I will write in the next page. I'm writing here sigma Vk T1 into Ik T2 for K is 4 branches is equal to sigma Vk T2 into Ik T1 for 4 branches. Okay, na? Do it now. Do it, everybody. Do it. First, find all voltages and currents here, everybody. Yes, see here everybody. See what I will do. First, I want all the elemental voltages and currents, so I will take a nodal here. See, I am taking nodal equation. So for this nodal equation is, yes, for this nodal equation, I am writing here for this network V minus 10 by 1 plus V by 2 minus 2 equal to 0. So if you solve 3V equal to 24, V equal to 8. So now we get V equal to 8 volts. That means this is 8 volts. This is also 8 volts. Okay, now because parallel. Now out of 10, 8 volts. See, out of 10 here, 8 volts means the drop has to be 2 volts. Now remaining currents I will find. Okay, let me find all the currents. So this is 2 by 1, 2 amperes. This is also 2 amperes. This is 8 by 2, 4 amperes. Okay, this is already given as 2 amperes. So I know I got voltage, current, voltage, current, voltage, current, voltage, current. Now see the next network. See, in this network, voltage sources have doubled. In this network, voltage sources have doubled. So node voltage also will double. Suppose if I take reference, then this V is automatically how much? 16 volts. You want your right equation. V minus 20 by 1, V by 2, minus 4, you will get 16 volts only. So that means this is 16 volts. Okay. If this is 16 volts, this is also 16 volts. This is also 16 volts. Now if this is 20, this is 16. Yes, if this is 20, this is 16. Yeah, if this is 20, this is 16. This has to be how much, sir? Yes, if this is 20, this is 16. This has to be 4 volt. Now again all currents. Chalo, now this is 4 by 1, 4 ampere, passive notation. Here also 4 amperes series. Now 16 by 2, 8 amperes. Okay, and this is 4 amperes. And this is 4 amperes. Okay, so we got all the elemental voltages and currents are. Now look very carefully. Luckily here everybody, yes, luckily here everybody, yes, you should understand that there is no change in polarity nor direction. Okay, there is no change in polarity nor direction. Okay, now yes, there is no change in polarity nor direction, sir. Yes or no? So I can easily prove. So what we have to prove now? Left hand side. Now listen, sir. Left hand side. Left hand side there are 4 branches. 4 branches I am writing like this: voltage into current, voltage into current, voltage into current. For 4 branches I am writing is equal to some watts you get. And right side also there are 4 branches in the same LTI network. Okay, network is same actually, but sources and excitations have changed. Excitations have changed. Now see, now left hand side, voltage at first time. See what are all the voltages in the first network? 10. This is branch 1, branch 2, branch 3, branch 4. Branch 1, branch 2, branch 3, branch 4. Voltage at first time 10 into current at second time 4. Okay, 10 into 4. Similarly, voltage at first time 2, current into second time 4. That is 2 into 4. This is also 2 into 4. Similarly, voltage at first time 8 into current at second time 8. Okay, this is 8 into 8. Okay, and then voltage in across this fourth branch 8 into current is again 4. So 8 into 4. This is also 8 into 4. Now come to right hand side. Voltage at second time into current at first time. Now see here. This first branch voltage is 20, current is 2. Voltage is 20, current is 2. Yes, voltage is 20, current is 2. Then this again, voltage is 4, current is 2. Right side voltage you have to take now V2, T2, branch 2 voltage in the second network. Okay. So now this is 4 and this is 2. Okay, this is again 4 and 2. Okay. And this is again voltage 16 and current is 4. Voltage is 16, current is 4. Okay, voltage is 16, current is 4. Okay, and then here again voltage is 16, current is 2. Voltage is 16, current is 2. Voltage is 16, current is 2. Okay, now you check both, sir. Yes, you check both. I want you to check both. You should get 144 watts. This is the proof. So left hand side is equal to right hand side. So we verified Teligans for time variance also. Teligans for time variance also we verified. See, very interesting problem. Okay. Same network, yes, but we are measuring voltages and currents at 2 different instances same time. Voltage at first time into current at second time is equal to voltage at second time into current at first time for all the branches. Observe carefully. Someone check these answers. I'm waiting. Yes, thank you, Imtiaz, etc. Everyone, thank you, sir. Some students are really writing answers, sir. I'm happy. Whether you get correct or wrong, I don't matter, sir. But as long as you are keep trying, and I'm very happy. Now here, now we are going to theorem 7. Very interesting. Theorem number 7. That is reciprocity theorem. Very, very interesting theorem. Reciprocity theorem. Okay. In any, very interesting, in any linear passive bilateral network, this is why it is very simple theorem. Okay. In any linear passive bilateral network, okay, the ratio of response, okay, the ratio of response to excitation, the ratio of response to excitation remains constant, okay, even if positions of source and load are interchanged. Okay. In any linear passive bilateral network, the ratio of response to excitation remains constant. The ratio of response to excitation remains constant, even if the positions of source and load are interchanged. Okay, in any linear passive bilateral network, the ratio of response to excitation remains constant, even if the positions of source and load are interchanged. Okay, even if the positions of source and load are interchanged. Okay, now see here, I will write here network figure A and same network figure B. Let us understand the meaning of this statement. So it is a passive network. Okay, it is a passive network. Okay, 1 dash 2 dash. I am showing like a 2-port network. Okay, I am showing like a 2-port network because excitation response terminals means 2-port. Again, same passive network. This is port 1 dash. This is port 2 dash. Okay, here what is the meaning? Yes, in any linear passive bilateral network, the ratio of response to excitation remains constant, even if the positions of source and load are interchanged. For example, here I am giving voltage V. Okay, here I am giving voltage V at port 1, which is allowing current I at port 2. Okay, here I am giving voltage V at port 1, which is allowing current I at port 2. Similarly, if I give voltage V at port 2, same current I should flow at port 1. Okay. If I give voltage V at port 1, it is allowing current I. Then if I give the same voltage V, let me correct it, same voltage V at port 2, it is also allowing same current I. Now the meaning, sir, now the meaning. That means if network is reciprocal, if the network is reciprocal, just if the network is reciprocal, then I by V is constant. I by V is constant. Okay, I by V is constant. Okay, then also by homogeneity, proportionality, I1 by V1 is I2 by V2. Okay, I1 by V1 is I2 by V2. Okay, see the meaning. Now you read the statement. In any linear passive bilateral network, the ratio of response to excitation remains constant even if the positions of source and load are interchanged. So here source is at port 1, load is at port 2. Similarly, source is at port 2, load also is port 1. That ratio of response to excitation. So here, for example, we took excitation as voltage, response as current. Here we took excitation as voltage, response as current. That ratio will be same. That ratio will be same. That is the meaning here. The ratio will be same. Okay, na? That is the meaning. Okay, na? That is the meaning of it. Okay. The ratio of response to excitation remains constant even if the positions of source and load are interchanged. Okay, even if the positions of source and load are interchanged. Okay, na? That is the meaning. That is the real meaning here. That is the real meaning. Okay. So now, also by homogeneity, like suppose here 10 volts is giving 2 amperes. 10 volts is giving 2 amperes. Here also 10 volts will give 2 amperes. Here also 10 volts will give 2 amperes. Very interesting, sir. Similarly, if 10 volts is giving 2 amperes, if 10 volts is giving 2 amperes, 20 volts will give 4 amperes. That is the meaning there. I1 by V1 equal to I2 by V2. Now some important points, sir. Okay, note some important points to remember. First point, this theorem is valid for networks only with one source. Very easy. Then this theorem is not valid for networks with the dependent sources. Yes, dependent sources, because dependent source can make network active now. So this theorem is not valid for networks with dependent sources. Now third, while writing the reciprocal network of the given network okay, while writing the reciprocal network of the given network, ideal voltage source, yes, ideal voltage source must be connected in series to target branch, and ideal current source must be connected in parallel to the target branch. Okay, while writing the reciprocal network of the given network, ideal voltage source must be connected in series to the target branch, and ideal current source must be connected in parallel to the target branch. Okay, ideal voltage source must be connected in series to the target branch, and ideal current source must be connected in parallel to the target branch. Okay, yes, parallel to the target branch. Then any linear passive bilateral network is by default reciprocal. Since reciprocity means passivity. Read these points. I will explain. Read these points. Still one more point I will tell. First, read this point, everyone. Okay. See, this theorem is valid for networks with only one source. Okay. Then this theorem is not valid for networks with dependent source. Okay. That is why very simple theorems are. And while writing the reciprocal network, yes, ideal voltage source must be connected in series to the target branch. Ideal current source must be connected in parallel to the target branch. Why? Because ideal voltage source internal resistance 0. You connect it in series, it will not alter the passive property. Similarly, ideal current source internal resistance is infinity. You connect it in parallel to any passive branch, it will not affect the property. That is the reason. Ulta you should not do. Don't put voltage source in parallel across passive element. That will be shorted in terms of resistance. And don't put current source in series to any passive element. That will be open in terms of passive reduction. Okay. And however, any linear passive bilateral network is always reciprocal since reciprocity means passivity. Now another point. What is another point? Now see here. The principle of reciprocity. Okay, the principle of reciprocity. Okay, the principle of reciprocity can be verified. Okay, for any passive network. Okay, the principle of reciprocity can be verified for any passive network as the ratio between response to excitation being constant. Okay, being constant by considering any parameter. Okay, by considering any parameter as input or output. Okay. Now the principle of reciprocity can be verified for any passive network. The principle of reciprocity can be verified for any passive network as a ratio between response to excitation being constant by considering any parameter as input or output. Okay. The principle of reciprocity can be verified for any passive network. Okay. As a ratio between response to excitation being constant. Okay. For any input or output. See, for example, in this discussion, excitation is voltage, response is current. Excitation is voltage, response is current. Okay. Yes, excitation is voltage, response is current. But you can take anything, like you can take excitation, current, response, voltage. You can take excitation, current, response, also current. Here also ratio. Suppose here voltage is input, current as output. Here you can take current as input and ratio voltage as output. Even that ratios will be same. Okay, that is very interesting. Like left side you take voltage as excitation, current as response. Right side you can take current as excitation and find voltage as response. Even then the ratios will be same. That is very interesting concept. Okay, na? That is very interesting concept that you have to understand even this fifth part. Okay. So now, sir, first question. Verify reciprocity principle. Yes, verify reciprocity principle for network below by determining current I. Okay, now this is the question. Verify reciprocity principle. Yes, verify reciprocity principle for the network shown below by determining current I. Okay, verify reciprocity principle for the network shown below by determining current I. Okay, verify reciprocity principle for the network shown below by determining current I. Okay, na, by determining current I. Okay, na. So now see this, sir. First step, see first step, step one. Okay, first find I normally. This current will be total voltage by total resistance 7 plus 2 in parallel to 6 into current division into opposite 6 by sum 6 plus 2 8. There's nothing but you get this as C here. This is again 7 12 by 7. Okay, this is 12 by 8. 56 plus 12 68. And this 8 8 will cancel. I think it will be 6 amperes. You check it. You check it, you will get 6 amperes. See, sir, I did current division. First, C is asking us to verify reciprocity principle. First of all, tell me, is reciprocity valid here? Yes, valid. Why it is valid? Reciprocity here valid because first of all, there is only one source and there is no dependent source. First of all, there is only one source and there is no dependent source. So please understand here, first of all, there is one source and there is no dependent source. Okay. Yes, first of all, please understand there is only one source and there is no dependent source. So reciprocity valid. Okay. Then first I want this current I. How to find this current I? How to find this current I? Okay. Yes. First I will find total current and current division. Now what is this total current? Total current is total voltage by total resistance. Total voltage is 68, but total resistance is 7 plus 2 in parallel to 6. 7 plus 2 in parallel to 6. So total voltage by total resistance, total current will come. Then current division between two parallel branches. This current will be total current into opposite 6. Opposite 6, sum 8. That will be 6 amperes. Okay, na? Now I am writing. Yes, now I am writing the reciprocal network. Now I am writing what? Reciprocal network of the given network. Okay, now what I am trying to do? Yes, now I am writing. Yes, and now I am writing reciprocal network of the given network. How to write this reciprocal network? See, first of all, remove the source. Voltage source na, removing voltage source means what we have to do? Short it. Okay na? Remove the source. So voltage source remove means short it. Now where we should connect and how? I gave in the third point na. Voltage source must be connected in series to the target branch. Voltage source must be connected in series to the target branch. Okay, voltage source must be connected in series to the target branch. Current source must be connected in parallel to the target. Okay, so what I'm doing here, our previous target was this one, na? So this voltage source must be connected in series to the target branch. Okay, this voltage source must be connected in series to the target branch. In series to the target branch. So this 1 ohm, 2 ohm, 3 ohm, 4 ohm, 5 ohm. This passive properties never change. So I should now connect 68 volts here. Okay. Yes. Now where I should find current? Where I should find current? Yeah, I should find current here. See the difference, sir. Previously 68 volts is here, current is here. Okay. Previously 68 volts is here and current is here. Okay, now. Now what I am trying to do? Yes, I put 68 volts here. I am finding current I there. I am putting 68 volts here and I am finding current I there. Okay, na? So let us also find this current, sir. Now this current again will be first total voltage 68 by total resistance. This time total resistance is 2 plus 2 plus. Now this branch and this branch are parallel. 7 in parallel to 6. 7 in parallel to 6 into current division. Current division. Now this current will be this total current into this total current to opposite 6. Opposite 6. Sum is 6 plus 7 30. Again you see this is 6 amperes only. Wonderful, na sir. So here reciprocity verified. This is step 2. This is step. Look here, I will explain again. Everyone look at the problem, I will explain again. Okay, now everybody, at least understanding now, sir. See, here I took 68 volts, here I got current. So here I took 68 volts, here I got. I did only current division, sir. Don't confuse. It will take time. See, immediately you may not get, but take time. See, I did just a current division. Okay, na? How the direction? Ah, yeah, yeah. One good dot, one good dot. Very good, very good. Coming there. See, Bamilendu Swine, how polarity? Ah, right. Sir, it doesn't matter, sir. It doesn't matter. Suppose, yes, one student is asking, sir, how you decided the polarity? See, previously in this 2 ohms branch, current is going down, na? Because he asked this direction and I got positive answer. That means really current is going down, na? So again in this branch, if current has to go down, plus should be down, na? Because source will drive the current down. Yes or no? That is the meaning. Suppose you do ulta also not a problem. Suppose you reverse the polarity of voltage, current direction also will reverse, but ratio will come same. Remember that. Suppose, sir, by mistake you took ulta polarity, current direction also will be reverse. That ratio will be same. That ratio we need to prove actually. Okay, na? So yes, see how I took that 68 volt polarity, because in this 2 ohm branch I took current direction down. He gave and I got positive answer. Positive answer means really current is going down. If really current is going down in the reciprocal network, plus should be down, na? Then only source will drive current downwards, na? That is the meaning. Okay, that is the meaning there. Okay, yes. It doesn't matter also. Suppose by mistake you gave ulta also, it doesn't matter. Ratio will be same. Okay, ratio will be same. Now next question. Verify reciprocity principle. Okay, principle for network below by determining voltage V, by determining voltage V. Okay, by determining voltage V. This also 1 ohm, 2 ohm I will take. Okay, na? And now I am asking to find voltage B. Chalo. Determine, verify reciprocity principle for the network shown below by determining voltage V. This is 123 amperes. So 123 ampere, 1 ohm, 2 ohm, 1 ohm, 2 ohm, 3 ohm, 4 ohm. It is a ladder network. And I want you to verify this theorem, reciprocity, by finding voltage V. Okay, na? Chalo, first step, everyone find V. Step 1. Find V. Everyone, I am giving 1 minute. Find V. Now see, I will see this is a ladder network now, sir. I told a shortcut. I will apply the shortcut to find B. See, first I will assume this is 1 ampere. Okay, I will assume I know I need to find voltage, but see, I will assume 1 ampere. When 1 ampere is going through 7, this is 7 volt. So automatically this is 7 by 2 ampere. 7 by 2 plus 1 KCL, 9 by 2 ampere. 9 by 2 plus 7 volts, total 23 by 2 volt. 23 by 2 volt by 2, it is 23 by 4 ampere. Now KCL, 23 by 4 plus 9 by 2, 41 by 4 amperes. That means here, because current source is given, C total current. Because current source is given, C total current. But if voltage source is given, C total voltage. Homogeneity. Now 40, that means here 41 by 4 amperes is driving 1 ampere here. Okay, 41 by 4 amperes is driving 1 ampere. Then 123 amperes will drive how much? That will be 123 by 41 by 4. 123 by 41 by 4. That is 12 amperes. But I need what? But I need V. So V is that current into resistance 4. That is 12 fours are 48 volts. See sir how I did 48 volts actually. Voltage na 48 volts. Homogeneity, that shortcut I gave you, na sir. I gave you that shortcut. Do you remember? All practice, sir. We are doing practice. And DC, if you know, sir, AC is easy. I will teach you. Only thing is phasor notation, J operator, etc. You have to learn. AC is more interesting. Okay, don't worry. But first, perfect in DC, we can enjoy a lot. Okay, na? Chalo, I'm going to the step 2. Okay, step 2. Yes, this is reciprocal network. Reciprocal network. Yes, I'm writing what? Reciprocal network I'm writing. Okay, na? I'm writing reciprocal network. Okay. Now if I write the reciprocal network, see first of all remove the current source. Remove the current source means open it. Remove the current source means open it. Remove the current source, open it. Okay. Yes, this is same 1 ohm, 2 ohm, 1 ohm, 2 ohm, 3 ohm, 4 ohm. Now where we should connect? In parallel to the target. Target was 4 ohm, na? Parallel to the target. Okay, this is 123. Now where we should find voltage? We should find voltage here. Chalo, everyone again try. Same style, try this voltage here. Everybody try. Quick. Yes, here also everybody, I will apply homogeneity. See, sir, I should find what this voltage, but here voltage cannot come because it is open. But let us say this is 1 ampere. If this is 1 ampere going through 3, this is 3 volt. If this is 3 volt across 2, oh, this is 3 by 2 ampere. Now 3 by 2 plus 1, this is 5 by 2 ampere. Now 15 by 2 plus 3, this is 21 by 2. 21 by 2 by 4 is 21 by 8. 21 by 8 plus 5 by 2 is 41 by 8 amperes. So no homogeneity. That means here 41 by 8 amperes is driving 1 ampere here. Then 123 amperes will drive how much? That is 123 by 41 by 8. That is 24 amperes. But I need V. But this V is I into R. R is how much? 2 here. That is nothing but 24 into 2. CSR 48 volts. Same answer. Fantastic answer we got. Fantastic answer. KCL KVL I did. KCL KVL. So here 123 ampere is giving there 48 volts. Here also 123 is giving 48 volts. So the principle of reciprocity is valid. The principle of reciprocity is valid. Okay, chalo, now I'm giving the next question. IES objective. Okay, use the data. Use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. R1, R2, R3, R4. R1, R2, R3, R4. This is 10 volts, 2 amperes. This is 20 volts. Now what is this current I? So answer this question. Use the data given in figure A to find current I in figure B. Okay, use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. Okay, use the data given in figure A to find current I in figure B. Okay, use the data given in figure A to find current I in figure B. So simple, sir. See, according to reciprocity, if 10 volts can give 2 amperes here. See now, if 10 volts can give 2 amperes here, 10 volts here will give 2 amperes here.
20 should give 4, but the given direction is opposite, na? So I is how much? -4. Yes or no? See, it is only reciprocity direct, sir. See, if 10 volts can give 2 here, okay? If 10 volts can give 2, so downward plus this side 10 volts will give this side upward 2. But 20 should give 4 upward. But this asked direction is opposite to practical, na? So I is -4. Yes or no? I is -4. Now I'm giving another question. This was also IS question. Same question, sir. Use the data given in figure A. Yes, use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. This is R1, R2, R3, R4, 10 volts, 2 amps. Now figure B. Use the data given in figure A to find current I in figure B. Yes, use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. Okay, here also see now everybody. See 10 volts is giving 2. Now listen carefully, sir. If 10 volts is giving 2. Now if I triple all the resistance, then current also become by 3. Current also become by 3. Yes or no? Now if 10 is giving 2 by 3 here. Now this side 10, okay, will give this side 2 by 3. This side it will give 2 by 3. Said it will give 2 by 3. Okay, now how much it is? 60. Now this 10 becomes 60. So 6 times. So this also become by 6 times. So this is again 4 amperes. But the asked direction and this is our opposite, na? Asked direction and this is opposite. So I is again -4 only. I is again -4 only. Very interesting, sir. I is again -4 only. I is again -4. Okay, see 10 is giving 2. If I triple all the resistance, this is 2 by 3. If 10 is given 2 by 3, this side 10 will give this side 2 by 3. But 60 will give 2 by 3 into 6, 4. But this direction and given is opposite. So I is again -4. Simple meanings are, see if I increase the voltage by 6 times and triple the resistance. I is V by R now. You are increasing voltage by 6 times, but triple the resistance. Current will only double, but opposite direction. Okay, current will only double, but opposite direction. Okay, na? That is the meaning there. Same. Use the data. Use the data given in figure A to find. Okay, to find current I in figure B. Yes, use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. Use the data given in figure A to find current I in figure B. Yes, I value in figure A, everybody. Yes, I value in figure A is, this is 1 ampere. Yes, I value in figure A is 1 ampere. Okay, everybody use the data given in figure A to find current I in figure B. Now I value in figure A is 1 ampere. So now you see this is 5 volts, 2 ohms, 2 ohms are, it is 1. Now here both 10 volts and 15 volts are there and I need I. Okay, everybody see here, everybody, in this problem, there are two sources, sir. You cannot directly apply reciprocity. We know reciprocity is valid only for single source network. Then what to do first? First apply superposition theorem. Chalo. Now here, first I will apply superposition theorem. Superposition theorem step 1. What is step 1? I will take 10 volts only. Okay, I will take 10 volts only. Listen here, sir. I will take 10 volts only and I will remove this 15 volts shorted. So I'll take 10 volts only. This is 2 ohm, 2 ohm, R, and let this be I dash. Let this be I dash. Okay. Okay, this is 2 ohm R, and let this be I dash. Okay. Now simple, sir. By the homogeneity, if I can give 1 ampere, if I can give 1 ampere, then 10 will give 2 amperes. So I dash we got. I dash we got. Okay, now step 2 is more interesting. Okay, now superposition theorem step 2. What is step 2? I will take now 15 volts only. So I will short this. Okay, now I will take 15 volts only. I will take 15 volts. This is 15 volts only. This is 2 ohm. This is 2 ohm. This is R. Okay, and let this be I double dash. Let this be I double dash. This is 2 ohms R, 15 volts, and let this be I double dash. Okay, let this be I double dash. Okay, now here let us again observe. Chalo, let us again observe. See from the data given. Okay, I need this I double dash now. See from the data given. Let me write the data. See now. Let us manipulate the data to get what I want. Okay, this is 2 ohm R, and this is 5 volts, and this is 1 ampere given now. This is given data. So see here, I need step 2. What is step 2? I took 15 and I need I double dash. Here I need. Chalo. Now see, 5 can give 1 here. So automatically this side 5 will give this side 1. This side 5 will give you this side 1. Okay, na? Yes. 5 can give 1, 5 will give 1. That is true. Okay. But he wants this current. Now how much is given here? 15, na? 15. Chalo, 15, 3 times. So this become 3. This also become 3. But he's not asking this current. He's asking current in this R ohms. So apply KCL. Chalo, if this is 3 amperes. Yes, if this is 3 amperes, this is 6 volts now. But because these two are parallel, this is also 6 volts. This is also 6 volts. If this is 6 volts, this is also 6 volts. This is 6 by 2. This is also 3 amperes. This is also 3 amperes. So this is 3, this is 3. Total it is 6 amperes. So I double dash is 6 amperes. Should see 5 volts is giving 1. 5 volts will give 1. 15 volts give 3. 5 volts can give 1. 5 volts will give 1. 15 will give 3. But he's not asking this current. Nah. This 3 will go here. 6 volts again. 3 will come. 3, 3, 6 will go here. So I double dash is 6 amperes. Okay, I double dash is clearly how much? 6 amperes. I double dash is 6 amperes. So by superposition. So by superposition theorem, this total current I is I dash plus I double dash. I dash is 2 amperes. I double dash is 6 amperes. Total 8 amperes. Total 8 amperes. Okay, that is a wonderful problem. Okay, wonderful problem. Okay, this is the last problem of the day, and we'll conclude this theorem. Yes, now again, use data. Okay, everybody, I'm writing this. Use the data given in figure A, data in figure A, to find I in figure B. In figure B. Passive network. Figure A. Same passive network. Figure B. So here 5 volts, 4 amperes, and this is 2 amperes. Now this is 15 volts. This is 45 volts. And I need this current I. Okay. Now use the data given in figure A to find current I in figure B. use the data given in figure A to find current I in figure B. Okay, use the data given in figure A to find current I in figure B. Okay, see here also we cannot apply directly reciprocity because there are two sources. Okay, so first step one, superposition theorem. So first I will apply superposition theorem. Step one. Step one, I will take 15 volts only. Chalo, I will take 15 volts only to this passive network, but I will remove the other side 45 volts. So this is 15 volts only, same network, passive network. Now let this current be I dash. So directly from homogeneity, what is this I dash? If I can drive 4, if I can drive 4, 15 can drive 3 times, not 12. 12. So I dash is 12. Now I'm going to step 2. So I'll take 15 volts only. Okay. Now I'm going to step 2. So I'm taking off 15 volts only. And I'm shorting this. Okay. 15 volts only and I'm shorting this. Okay. Let this be I double dash. Okay. Same network. Let this be I double dash. Okay. Sorry, 45 now. Let me correct it. Correct. Yeah, I'm taking off 45. See, first step. See, in this first step, I took 15, removed 45. Then if 5 can give 4, 15 can give 12. That is over. Second step, I will take 45, but I will remove 15. So I need this now. Now let us take the data. See, the data given, I will manipulate to get what I want. Listen carefully. See, the data given, I will manipulate. Because this is 5 volts and this is how much? 2 amperes. Now listen. So if 5 volts can give 2 here, now this side 5. See, this side 5 volts can give this side also 2. Can give this side also 2 amperes. Can give this side also 2 amperes. 5 volts can give this side, 5 volts also can give 2. Okay. Then if you reverse the polarity, chalo, if you reverse the polarity, if I ulta the 5 volts, yes, if I ulta the 5 volts, yes, if I reverse the 5 volts, current direction also will reverse. Direction also will reverse. Okay, 5 volts will give. But here, how much is the target? 45, 9 times. Yes, 45. I'll make this as 45 volts, 9 times. So this becomes 9 to the 18 amperes. 18 amperes. 18 amperes. Okay. Now, but this is going this side. But here, asked is ulta na. So I double dash is automatically how much? I double dash is minus 18. Yes or no? Because this is the actual direction. This is ulta. So by superposition, yes, by superposition, I is I dash plus I double dash. One is plus 12, one is minus 18. So answer is minus 6 amperes. Chalo, minus 6 amperes. Okay. Yes, doubts you can ask Vishnu. What is your doubt?
Sir, my doubt is in time invariance. Sir.
Which topic?
Time invariance.
What is your doubt? Tell me. You express it out. I know the meaning. Now tell me doubt.
Sir, I have the doubt regarding that formula alone, sir. Why are we taking voltage in first circle and multiplying with second? Like, how is that verifying the time variance?
See, time variance in excitation. Time variance in excitation because excitations are changing in time. Actually, they may be a ramp function. Na? Imagine that voltage at the we are representing, maybe their original functions are ramp functions. Like at some second, this is the voltage, this is the current. At 10th second, this is the voltage and this is the current. So time variance in excitations, but LTI network is same.
Yes, sir.
Understood?
Yes, sir.
Okay.
So that's why, like, For instance, you're taking voltage in the first circuit and you're multiplying with the current around across the same element in the next instance.
Second circuit. Correct. Yes. Similarly, voltage in second time into current at first time for all the branches is equal to voltage at first time into current at second time for all the branches.
Okay, sir. Sir, why don't they check it as like V1 I1 equal to V2 I2T?
That is already there, but this is something extra we are learning. Same network at two different times also we can prove. That is the law of conservation of energy. V1 I1, V2 I2 we already proved in this big problem. Na? In this big problem we already proved. Na?
That is intelligence theorem alone.
This is also another property of Teligens's theorem for time variance in excitations.
Okay, sir. Okay.
Okay?
Yes, sir.
Okay.
Thank you, sir.
Right. Shiva, what is your doubt, Shiva?
So same thing, sir. Sir, here, like we can conclude that the power at any instant the circuit is constant. That's what we try.
Correct. Simple. Yes.
Okay.
It is homogeneity also. You can also argue that it is homogeneity. But law of conservation of energy will never fail.
Yes, sir. Okay.
Okay?
And then one more, I need a conclusion, sir. So if power absorbed by a source is negative and power delivered by the source, we can take it as positive.
That is true. What is asked? Power absorbed or delivered. If it is a source, power delivered is correct, positive. And similarly, if a sink is there, for sink power absorbed, absorbed is positive.
Okay, sir. Sir, and then the first problem of Teligens's theorem.
Tell me, what is your doubt?
Sir, there how you got that 54 volt across
Write a KVL. See, write a KVL. Suppose you don't know. Let us say this is some X volts. Okay, you take like this X. So write a KVL. See, starting here, minus 42 plus 24 minus 36 plus X is equal to 0. Nah? So X is 54.
Okay, sir.
Okay, plus 54 confirm. Yeah, plus 54 confirm that my polarity is correct and I took like 54 only. That is the meaning.
So then last doubt, sir. So that 123 amps current source problem.
Tell me homogeneity.
Sir, after converting the network, like the direction of current source should be in downwards, no, sir? Why you?
No, that is what I take. If you want, you take down. Yes, nothing wrong. If you want, you take down. Then polarity also will be ulta. Ratio will be same.
Okay, sir. Because like in the previous, in the original network, current is flowing in the downward direction for 4 ohms. So
You can. But this is a current source in parallel to the target branch. Even if your argument is there, even if your
okay, sir, got it.
Then only it will go the same direction. Yes or no?
Okay, sir, got it. Yes,
Right.
Thank you, sir.
Right. Pratyush.
Hello, sir.
Tell me.
Sir, in case of Teligens's theorem problem, 20 volts and 10 ohms and E is there, no, sir. Find E. Sir, their power absorbed is given as 10 volts, no, sir.
10 watts. Power absorbed is 10 watts.
10 volts, sir. 10 watts, sir. Sir, then power delivered should be 10 watts, no, sir.
No, power absorbed by E alone is telling, not power absorbed by the total network.
Okay, sir.
Power absorbed by the battery alone is given, not power absorbed by the total network.
Okay, sir. Okay. Sir, another one, sir. In
Tell
case
me.
of maximum power transfer theorem, for today's first term, sir.
Tell me, what is your doubt?
Sir, in that case, we have taken that voltage is half of the source voltage, no, sir.
Okay, correct.
Sir, but that is possible only when load and source resistance are equal, no, sir. But here that is not equal.
Not equal, we cannot argue. See, whatever may be the condition, if really Pmax has to occur, the combined equivalent resistance, including the battery, has to be same. There is a meaning there. The combined equivalent resistance, including the battery, has to be same.
That means battery has internal resistance should be considered like that, sir.
That is the meaning. That means the combined network, load network resistance, including the source effect, should be same. That is why reduction not possible. That logic we applied. Under Pmax theorem, one thing is for sure. This combined resistance, including the battery, should be this. But we cannot simplify like that. So 50% drop is true.
Okay, sir. Okay. Sir, can we find here the battery's internal resistance, sir? We equipping to 10 ohms.
No, it's not about that. Whatever may be the network, you may or may not take. Whatever may be the equivalent, the combined resistance of this, including the effect of E or internal resistance or anything, should be same. Then 50% drop is true.
Okay, sir. Okay, sir.
Okay?
Okay,
Yeah.
yes, sir. Thank you. Thank you, sir.
Yogesh.
Hello.
Yeah, tell me, Yogesh.
Sir, when we are calculating the independent source value, sir, can we
Okay.
treat it as independent? Sorry, when we calculate dependent source value, sir, after that we can treat it as independent source, sir.
But effect of resistance do exist. In equivalent, we cannot simplify. We can treat it as a source or sink, but we cannot simplify as a passive reduction because its internal resistance is a subcircuit. Until subcircuit is declared, we cannot argue like that.
Okay, sir.
Okay, that is a source with some internal resistance which can be modeled in a subcircuit only. If subcircuit is not declared, we cannot argue like that.
Okay, sir.
Okay, right. Then Akshay.
Thank you, sir.
Right. Akshay.
Hello, sir. Sir, in that maximum power transfer second problem, the static VI cara. Sir, here I is equal to -6. How will we take the direction in that circuit? Sir?
See, he gave this direction like this, sir. He gave, that means this is a reference direction what he gave. That means considered as positive. For that, minus of this direction means it should go right side.
Oh.
Because the box we modeled into Thevenin's theorem. Minus of this direction means it should go outside the box.
Okay, sir.
Okay.
Got it, sir. Thank you, sir.
Sangeet.
Hello, sir.
Tell me.
Sir, I just have a doubt regarding that 123 ampere ladder network question in the reciprocal network.
Yeah, tell me what you have to tell me.
Just so that how did you find the current value? I just want to know. I understood the original network, but the reciprocal network I got confused a bit.
See, first of all, 123 amperes you removed, so open this. Place this 123 in parallel to the target branch.
Okay, sir.
Okay. Now
Yes,
again,
sir.
I want this voltage V now.
Yes.
So here I started by homogeneity by taking this as 1 ampere.
Okay, sir.
So 1 ampere is going here. So 1 plus 2, 3 volts will come here.
1 plus 2.
Because 1 ampere is going like this only now.
Yes, sir.
So 1 1s are 1, 1 2s are 2, 1 plus 2 total 3 volts.
Okay. That full mesh, that mesh is we are
Yes.
assuming.
Again, this is 3 by 2 KCL. 3 by 2 plus
Okay.
5 by 2. Like that KCL KVL from left side. Previously KCL KVL from right side. Here KCL KVL from left side.
Little confused, sir. Once more, please. Sorry for the.
This is 3 by 2. This is 1 we got now.
I got the 1 ampere. We get 2 volts. Then the 3 by 2 part. Okay.
See, this is 1 volt plus 2 volts. This branch and this branch now are parallel actually.
Okay, sir.
So this is 3 volts. So here also 3 volts will come. Now 3 by 2. Current is how much? Voltage by resistance 3 by 2.
Okay.
So now again KCL here. 3 by 2 plus 1 is 5 by 2 ampere.
Okay, sir. From that point, I understood little. Still, that initial part is little confusion.
Which
We
part?
assumed 1 ampere.
That is only homogeneity random. Actually, 1 ampere is not the answer. I took 1 ampere to develop what current is required here. So I took 1 ampere to understand how much current will drive that 1 ampere.
Sir, that part I understood. I understood the homogeneity part. Just that how you did the development part. I'm little confused.
See, you start with an assumption that you take 1 ampere here.
Okay.
It is homogeneity. Or you take 2 amperes also, no problem. But you start with an assumption that this is 1 ampere. So
Okay.
once it is 1 ampere, I slowly built up KCL KVL to understand that 41 by 8 amperes is driving 1 ampere here.
Okay, sir. Okay.
If 41 by 8 can drive 1, I took 1 because it is easy to calculate initially. So 41 by 8 will drive 1. Then 123 by 123 will drive how much? 24, like that.
Okay. Fine.
Okay, that one is our test signal. Okay.
Okay, sir. I got it.
Okay.
Thank you.
Right. Then this Bimelendu swine.
Hello, sir. Good morning, sir. Sir, doubt in that maximum power transfer. First question.
Okay, tell me.
Okay, sir. Here you taken VS by 2.
Yes.
But if I convert that network to some Thevenin's voltage and Thevenin's resistance,
100% you will get. 100% you will get. Suppose I will give you the hint. I'll give you the hint. You do it and tell me tomorrow. See, what I will do is this right side. First, I will simplify. See, left side network will be same.
yes.
This is 20 volt, and this is 10 ohm.
So right side, first I will convert this box into Thevenin's equivalent. Let us say this is the box which is the load network. I'll first simplify into Thevenin's. What will it become? Now if you look at this box from here, open circuit, Thevenin's resistance will be 20 in parallel to 5. Okay, that is 100 by 25. This is 4 ohms. This is 4 ohms. And this voltage will be how much? This voltage will be how much? Thevenin's voltage. See, if you open this voltage division between E 20 and 5, so this voltage will be total voltage E into same
0.8.
Same is 20 by sum is 25. Okay, 4E by 5. Yes or no? You will get 4E by 5, like 0.8 E. Okay, now 4E by 5 you will get. So this is 4E by 5.
Yes, sir.
4E by 5. Now load has got two components. We have reduced the load into two components. Three components became two components. Okay, now? And first I will find the current expression. This current is what? 20 minus 5 whole by 14 you will get.
Yes.
Okay, if you take LCM, that is 100 minus 4E by, this is nothing but 14 5s are 70. Or you can take 50 minus 2E by 35. Now what is the load power expression? Load power expression is one is I square into R. One is 4E by 5 into I. Yes or no? That is the total power. So you substitute this I here. That is I square. That is 50 minus 2E by 35 square into 4 plus 4E by 5 into I. But again I is 50 minus 2E by 35. Now for P max, now for PL max, you do dPL by DE 100%, you will get E as 7.5.
Sir, in that problem, you taken VS by 2 for if there is some dependent source, then we can't say no, this is the internal.
Even dependent source is there, anything is there, but the combined equivalent resistance of the subnetwork should be equal to the total resistance of the supply. That is, both should be equal, then only Pmax will occur. Under that condition, 50% drop. Yes.
Means this is for easy calculation.
Yes, correct.
And in SC circuit also same.
Same. AC, their real power, that I will tell you later. Real power, that concept we'll talk. Okay?
Thank you, sir.
Okay, right. Okay, tomorrow again 7 o'clock, everybody.
Sir, one last doubt, sir.
Tell me.
Sir, the fourth point of reciprocity theorem.
Fourth point, wait. How to come to my, wait.
No, sir, I'll just read out. Could you please?
Fourth problem of reciprocity. Tell me what is your doubt.
Fourth point. Any linear passive bilateral network is by default reciprocal.
See, passivity means reciprocity. Reciprocity means passivity actually. So yes, here any linear passive bilateral network is reciprocal means yes, reciprocity means passivity. That means all passive bilateral networks are reciprocal. That is the rule. Unilateral is all passive bilateral network are reciprocal.
Okay, sir. So,
that is why these conditions will come later in two ports also.
Okay, sir. What passivity signifies?
Passivity means passive, only passive elements. That means the box inside. See here also, excluding this 68 volts, remaining should be passive.
Oh, okay, sir.
Here also, suppose excluding this. Here also excluding this box, everything only one source. This box should be passive only. No dependent sources, no initial conditions like that.
Okay, sir.
Okay.
Yes, sir. Thank you, sir. Yes, sir.
Okay.